Hey everyone, welcome back. Last time we explored what neural networks are and how they're inspired by the brain, as well as the general structure involving input, hidden, and output layers. Today we're going to dive deeper into those layers, not just what they are, but how they work together to make a neural network function. We won't get too technical, but we're going to peel back some layers to really understand the inner workings in a simple way. So let's jump right into these details and see how all these parts, layers, neurons, connections, and activation functions come together to create the magic behind neural networks. Part 1. Layers. Let's start by imagining a sandwich. A neural network is made up of layers, just like our sandwich has slices of bread, maybe a few layers of cheese, some lettuce, and whatever else you like. In our neural network sandwich, we have 3 important layers. The first layer is the input layer. It's like the bottom slice of bread. Everything starts here. This is where our network takes in the data. Think of it as the layer that's paying attention to all the ingredients we give it. But let's get a bit more concrete. How do we actually create this input layer? In an actual neural network, especially if you're coding it in Python, this input layer is defined using a framework like TensorFlow or PyTorch. Imagine you're writing a bit of code. The input layer is where you tell the network what type of data it's going to get. Let's say you're working with an image. It could be as simple as specifying the size of that image, like 28 by 28 pixels for a grayscale picture. This input layer is defined in code to accept this data. And that's really what makes it different from the other layers. It doesn't do any transformations or computations. It's just there to receive the data. It's like saying, okay, here's the information, let's get started. It's the entry point to the network, setting the stage for everything else that comes afterward. Now, let's talk about the hidden layers. These are where all the real action happens, where the network learns to understand and transform the input data. In code, hidden layers are defined much like the input layer, but with a big difference. They do all the heavy lifting. When you create a hidden layer, you're essentially adding layers that apply calculations to the input. For example, in Python, you might use something like dense, units equals 64, if you're using a library like TensorFlow or Keras. Here, units refers to the number of neurons in that layer. And each one of these neurons takes in data, does some math, and then sends it along to the next layer. The key here is that hidden layers are where patterns are learned. They're not just passing information along, they're changing it, transforming it, and making sense of it. This is what sets them apart from the input and output layers. They take the raw data and layer by layer, break it down into more meaningful parts. If our network is trying to recognize an image of a cat, one hidden layer might recognize edges, another might find textures, and the deeper we go, the more abstract the features become, like recognizing whiskers or an entire face. But here's the really fascinating part. This is also the layer that even the best scientists can't fully explain. Remember when lawmakers asked the creators of ChatGPT and other AI models how they do what they do? Sometimes even they don't have a clear answer. The hidden layers are like a mysterious black box. Information goes in, it gets transformed in ways that even experts struggle to describe, and somehow it works. It's this complexity and the ability of hidden layers to learn subtle and intricate patterns that make neural networks so powerful, yet so elusive. And when you hear about a new AI model having billions of parameters, they're talking about all the connections and weights within these hidden layers. Each of these parameters is like a small knob that adjusts how the information flows through the layers. The more parameters there are, the more detailed and refined the network can be in learning from the data. So those billions of parameters are really the key to why modern large language models, or LLMs, like the latest version of ChatGPT, are so effective. They have an incredibly vast number of these connections that allow them to understand language at a deep level. Finally, we have the output layer. This is the last slice of bread on top where everything comes together. It's where all the hard work of the hidden layers finally pays off, and the network makes a decision or gives us an answer. If we go back to our image example, this is the point where the network might say, "This is definitely a cat," or "Nope, this is a dog." In code, the output layer is defined similarly to the other layers. But the main difference here is the purpose. It's meant to produce the final result. It could be a single value, like predicting the price of a house, or a category, like identifying an image as a cat or a dog. The output layer is where all the transformations and calculations from the hidden layers are combined to make the final prediction. It's also the layer that defines the type of problem you're trying to solve. For example, if we're building a network for classification, like deciding if something is a cat or not, we'll use a different kind of output layer compared to if we were predicting a continuous value like temperature. And then finally, when everything is said and done, the entire neural network, input, hidden layers, and output, works together like a well-oiled machine to take raw data and turn it into meaningful results. The output layer is like the culmination of all the understanding built in those hidden layers. It's where everything clicks and the network gives us something we can use, whether it's a label, a number, or even an entire conversation, like the kind you'd have with an AI assistant. Part 2. Neurons and connections. Now let's dig a bit deeper. Every layer, whether it's input, hidden, or output, is made up of what we call neurons. You can think of neurons as little messengers, each one carrying a piece of information. Imagine them as workers in a big office building, each with a specific task to complete. So, what do these neurons do? Well, in the input layer, each neuron picks up a bit of information, like a worker receiving a specific task list for the day. If we're working with an image, for example, each pixel would be picked up by a different neuron, processing just that tiny part of the whole picture. The task at this stage is simple. Just take in the data. Then, as this information moves through the hidden layers, each neuron works on it. It's like passing the information from one department to another within the office building. Each department has a role. Some might focus on recognizing basic shapes. Others might pick up more complex patterns. Imagine that the first department works on recognizing edges, the next on identifying textures, and finally, another department might be figuring out whether what it's seeing is part of an ear or a paw. The deeper the information goes through the layers, the more abstract and complex the features it can identify. This step-by-step transformation is what gives neural networks their power to recognize and learn complex patterns. Each neuron also has something called a bias. Biases are like giving certain pieces of information a little extra push to make sure they go through. Imagine if some departments in our office building need extra help to meet their deadlines. Biases provide that extra nudge to get things moving. They help ensure that even if the initial data isn't strong enough on its own, it can still influence the outcome. This is really useful when we want the network to always have a minimum level of activity, helping it learn from even subtle signals. The information doesn't just jump from one neuron to the next without a system in place. Connections between neurons help move this information through the network, and these connections have what we call weights. Think of weights like a traffic light system. Some pieces of information get the green light to move forward easily, while others might be held back or slowed down. These weights are incredibly important because they help the network decide what information is crucial and what can be ignored. When a neuron receives information, it multiplies it by the weight of that connection. If the weight is high, that means this information is important and should be passed along strongly. If it's low, then the information doesn't matter as much. What makes all of this really powerful is that each of these weights and biases gets adjusted during training. This means that the network learns over time which information is important and which isn't. It's like our office workers gradually getting better and better at understanding what's critical for their job until they can make decisions incredibly quickly and accurately. This constant adjustment process is what allows neural networks to become so effective at tasks like recognizing faces, understanding speech, or even generating text like ChatGPT does. So, to summarize, each neuron is like a worker. Each connection has a weight that tells us how important the information is, and each bias gives a little boost to certain pieces of information. Together, they transform the data step by step through each layer until we end up with a meaningful output. It's a beautiful process of many simple units working together to create something incredibly complex. Part 3. Activation functions. Okay, here's where it gets fun. Let's talk about activation functions. It sounds complicated, but let's think about it in simple terms. Imagine you're trying to decide whether to go out for a run. You check the weather, see how you feel, and maybe even think about how much time you have. This decision-making process is a lot like what an activation function does. It helps the neurons decide, should I pass this information along or not? Without activation functions, our network would be pretty useless. It would just do some basic math and call it a day. Imagine a light switch that's either always off or always on. Without an activation function, that's essentially what our network would be like. Only capable of very basic and linear operations. Activation functions give the network the power to make decisions. Almost like turning on a light bulb when something is important, or flipping a switch depending on the information being passed through. Activation functions also make the network capable of learning complex, non-linear relationships in the data. Let's say we're trying to separate pictures of cats and dogs. In real life, these pictures aren't simple. They don't fit into neat little boxes, and there's no clear, straight line that can divide them. Activation functions help the network create these complex boundaries. Imagine being able to draw curves and squiggles that perfectly fit around all the cat and dog images to separate them. That's what activation functions make possible. There are a few common types of activation functions, and each one has its own unique characteristics. ReLU, rectified linear unit. It's one of the most popular activation functions because it's simple, yet effective. You can think of ReLU like a filter that lets positive information pass through, but stops anything negative. This simplicity helps the network focus on important signals and ignore the noise. And that's why ReLU is widely used in hidden layers. Sigmoid function. This one makes information smooth and scales it between 0 and 1. More like a yes or no situation, which helps make decisions clearer. It's often used when we need a probability-like output, for example, determining if something is either a cat or not, as it conveniently scales the value to something between 0 and 1, just like a probability. Tan, hyperbolic tangent. It's a lot like the sigmoid function, but instead of being limited between 0 and 1, it ranges from -1 to 1. You can think of tan as giving us a more complete picture. Instead of just yes or no, it can express negative, neutral, or positive. This helps in cases where we need to know not just if something is positive, but also how strongly positive or negative it is. Activation functions are crucial in giving our network the flexibility it needs to learn from all kinds of data. They allow the network to combine inputs in a way that isn't just a simple linear combination, but rather something far more flexible. It's what makes neural networks different from just doing basic math. They add layers of decision-making and complexity, which makes them capable of tackling incredibly challenging problems like understanding speech or generating realistic images. So to sum it all up, A neural network is like a big team working together. You've got your input layer taking in information, hidden layers working behind the scenes to understand it, and the output layer giving us a result. Neurons pass along the information, and those connections with weights help decide what's important, while biases adjust the output to give the network more flexibility. Finally, the activation functions make the decisions, turning certain pieces of information on or off like lights in different rooms of the house. And there you have it. That's a quick look at the structure of a neural network. Next time, we'll be looking into how these neural networks actually learn from data. Until then, take care and keep exploring.